Yes, so dear student, I Rakesh Jain from Ganware University. Today I am going to teach you about mass defect and binding energy. So after the completion of this lecture, you will easily understand that neutrons and protons, whenever meet in the nucleus, what will happen, and how we can break the nucleus into its nucleus of any atom into its protons and neutrons, and what kind of energy we should use for that, and what is the name of that energy, and what is the unit of that energy. After the completion of this lecture, you will easily understand the formula of binding energy and mass defect and how to use it in practical numericals. So let us start with, first of all, just see this MS Pen file. So this is our topic, mass defect and binding energy, and I am going to write down to the date, that is 21 June 2020. So first of all, what is the meaning of mass defect? So in a whenever whenever neutrons and protons meet, or we can say combine in nucleus, then there is some mass loss. So that is known as mass defect. Mass defect means defect in mass, that is loss in mass. So when it will happen? Whenever the neutrons and protons meet or combine in the nucleus. So whenever neutrons and protons meet, that is combine, meet or combine in nucleus, then some mass loss, that is mass defect. And any, so in a very simple definition, what is mass defect? We know that each atom have some nucleus. So in the nucleus, protons and neutrons are present, and they can combine to each other. They can meet to each other. So whenever they meet, they combine. As a result, there is some mass loss, and that is known as mass defect. So let's suppose, so in terms of the numerical representation, or in terms of the formula, let's suppose capital M represent the mass of nucleus. Capital Z represent the mass of proton. Capital N represent mass of neutrons. Instead of capital, we can use the small letters. Why? Because we know that the mass of nucleus is far apart, that is very large compared with those. So we can use here small z also, and here small n also. So no problem. Okay. Otherwise, you can use the capital. There is no problem to use these letters. You should know about the abbreviation. NP is your our mass of protons. NP is our mass of proton. Mass of proton. NP is our mass of proton. And for the mass of neutron, we use Mn. For the mass of neutron, we use Mn. The subscript is so that it is related with neutrons. And this Mn is mass of neutron. This is mass of neutron. And this capital M is mass of nucleus, Z is mass of proton, capital N is mass of neutron, Mp is mass of proton, Z is the number of protons. Number of, and capital N is number of neutrons. Okay. Np is the mass of proton and Mn is the mass of neutrons. Then how the mass defect can be represented by? So mass defect for the, as in the terms of abbreviation, the mass defect abbreviation is del M. Del M is the representation of mass defect. And in the terms of formula, we can see mass defect, that is del M, is actually equal to ZMP, that is number of protons multiplied by mass of proton, plus NMN, that is number of neutrons multiplied by mass of neutrons, minus this total sum terms, minus from subtracted minus capital M, that is mass of nucleus, and this is known as this capital M can also be known as actual mass. This capital M is also known as actual mass, and this ZMP plus NMN can also be termed as calculated mass for the nucleus. This together, if I write down ZMP plus NMN, that is your calculated mass of the nucleus, and capital N is your actual mass of the nucleus. So calculated mass of the nucleus minus actual mass of the nucleus is termed as del M, that is mass defect, and it can only happens because neutrons and protons combine or meet in a nucleus. So this formula is known as the formula for mass defect. This is known as formula for mass defects. And the unit is atomic mass unit. Atomic mass unit, AIM, is the standard unit for the mass defect. Now we know that the total protons and neutrons are actually given as Z. For example, I have lithium. For example, lithium, hydrogen, helium, lithium. So lithium, how we can show the lithium of periodic table? From the periodic table we can take the, so it will be present as 3 number and its atomic mass is actually 7. So 3Li7 is for lithium. So 3 is what? 3, this whatever write down at the left hand side of any atom or any nucleus from the periodic table, then this one is known as Z. This left hand side term is known as Z, that is number of neutrons, number of protons. This Z is number of protons, remember this. This atomic mass is actually your A. It can be represented by A. This show you the number of protons plus number of neutrons actually. So this A is equal to, that is number of protons plus number of neutrons. This A is equal to actually Z plus capital. So whenever you are going to solve any numerical, remember, whenever you talk about any kind of numerical like lithium, beryllium, boron, helium, for any kind of term, then remember this thing, the left hand side subscript to show you the number of protons. Okay, the right hand side upper power term show you the value of A, that is number of protons plus number of neutrons. So we can easily calculate that what is N. N is equal to A minus Z. For example, let's suppose I take the example of helium. Let's suppose. So hydrogen, helium. So the in periodic table it will comes at the number of 2. So how we can represent the helium? So helium can be represented by 2He4. In numericals, it will be given to you that for which thing you have to find out the mass defect. So 2He4, 3Li7, so any kind of beryllium, if that is beryllium, then it is also given that 4B and 8, it will automatically give you. So now, what is the Z? So Z is this one, that is this atomic number can also be known as the number of protons. So Z is 2, Z is 2. If you are getting confused from this symbol of Z, then you can use this very simple symbol of Z. So Z is your 2 for this. And what is your N? What is your A? So A is 4. It means what is the number of neutrons? N. So N is equal to A minus Z. And that will be equal to 4 minus 2. When we will solve after the completion of this theory, we will take the example of lithium, helium, beryllium. So you will easily find, again see this one, so repeat, and then you will easily solve the numericals. You will easily calculate the remaining thing, whatever frequently asking numericals. So N is equal to 2, Z is equal to 2, right? NP, Mn, and capital M will be given in the numericals. If then use those terms and find out the mass defect. We will see later on the numerical on this topic. For this example, what is capital N for the lithium? Z is equal to 3, N is equal to 7 minus 3, and that is equal to 4. So, number of neutrons N we calculate, that is 4. Number of protons Z we have already been calculated, that is 3. MP, Mn, and N usually given in numericals, and we can easily find out what is the mass defect in atomic mass unit. Now, what is the binding energy? So, see this one. What is the binding energy? What is the binding energy? Binding energy, we can say just a little bit related with the completely related with this mass defect, and actually correlate with this mass defect in opposite terms. So binding energy is the energy which is required to break the nucleus of any atom into protons and neutrons. So binding energy, I just write down the definition of this binding energy. Binding is the required energy to break the nucleus of any atom into binding energy is the required energy to break the nucleus of any atom into protons and neutrons. Neutrons. This is the standard definition for the binding energy. How we can calculate the binding energy? So binding energy can be calculated with this formula, that binding energy is equal to del M multiplied by C square. Del M is your mass defect. Del M is mass defect multiplied by C square. Multiplied by C square. So this is the standard formula for the binding energy. This is the standard formula for the binding energy, and the unit for the binding energy is electron volt. But when we will put the value, calculated value for this C square, actually this C square is equal to 931.5 mega electron volt. 931.5 mega electron volt. Mega. I just write down the pronunciation for this MEV, that is mega electron volt. So actually mega electron volt. So when we just put the value of this C square over there, then now the binding energy is actually equal to del M multiplied by 93.5, and the total overall unit for this binding energy then will be, and this total binding energy unit will be mega electron. This is the standard formula to calculate the binding energy of any numerical. So these two formula which I have, which you just see on this screen, that is mass defect. Del M is equal to Z MP plus N Mn minus capital N, and binding energy, that is del M multiplied by 931.5 mega electron volt. So you should calculate these values and find out the answers of different kind of numericals which are frequently asked in main examinations. So let me solve some numericals on this. Before going to solve these numericals, once again I just repeat the terms which are related with mass defect and binding energy. So mass defect and binding energy, actually these two terms are related with the nuclear science. We know that any atom of the periodic table have some nucleus, and in nucleus protons and neutrons are present. So whenever those neutrons and protons present in the nucleus meet or combine with each other, then there is some loss of mass. That loss of mass can be termed as mass defect, and that mass defect depends on the total mass of the nucleus, the mass of the protons, the mass of the neutrons, the number of protons present in the nucleus, and number of neutrons present in the nucleus. So the numerical formula to calculate the mass defect, the standard unit for the mass defect is atomic mass unit. That loss of mass in terms of atomic mass unit. So the mass defect is equal to standard formula. The mass defect can be abbreviated by del M, and del M is equal to Z MP plus N Mn, and this total term minus capital N. This capital N is actual mass of the nucleus. This Z is the number of protons. This N is number of neutrons. MP is mass of protons. Mn is mass of neutron. This mass defect when multiplied by C square, that is 931.5 mega electron volt, then it will be termed as a binding energy. So the standard formula for the binding energy is 931.5 multiplied by del M, where del M is your mass defect in atomic mass. And the overall unit for the binding energy is mega electron volt. Mega electron volt in terms of the definition. So binding energy is the required energy to split the nucleus of any atom or to break the nucleus of any atom into protons and neutrons. So that is known as binding energy. Now we have to solve some numericals. So let's start some numericals. Let's save this file and then we will start. Yes. So I just write down one numerical. This numerical very carefully. Calculate the binding energy and calculate the mass defect and binding energy. Calculate the mass defect and binding energy for helium and in bracket it is given helium as 2He4. As I have already been told that helium can be termed like this one. So 2He4. So calculate the mass defect and binding energy for helium when the mass of proton is 1.0072747 AMU. And the mass of proton is 1.00, and the mass of proton is 1.00727 AMU, and mass of neutron is 1.00866,490 AMU, and the mass of nucleus, the actual mass of nucleus, actual mass of nucleus is 4.001560,1506 So now we have to calculate the mass defect and binding energy for this numerical. So this is a numerical which is in front of you, that calculate the mass defect and binding energy for helium 2He4, where the mass of proton is this and mass of neutron is this and the actual mass of nucleus is this. Okay, first of all, we should use the same formula. First of all, I just represent you the first formula how we can calculate the mass defect. So I just copy and paste this formula in that second slide, so we can easily find out the answer of this question. First of all, we should calculate the mass defect, and we know that what is the standard formula for the mass defect. So we should require for this mass defect Z. We should require for this mass defect NP. We should require the value of Mn. We should require the value of capital N. And we should have about capital N. If we have all these values, definitely we can easily calculate the mass defect. So first of all, let's see. We have to calculate what is the nucleus, that is of helium. Which one is the atom? Atom is of helium. So first of all, this value is termed as Z. So in this value, the number of protons, that is the atomic number of any atom, is actually given as 2. So here Z is equal to 2. Now this upper term is the atomic mass, which is given as A, that is actually equal to number of protons plus number of neutrons. That is actually equal to Z, that is number of protons, plus N, that is number of neutrons. So Z plus N, that is equal to 2. Z plus N. So what is A? A is given as 4. What is Z? Z is given as 2. Now we can easily calculate for this question what is your capital N. So definitely the number of neutrons is equal to 4 minus 2, that is equal to 2. So it means capital N is 2 again. Now NP is what? Mass of protons, and here it is written that mass of proton is 1.0072767 AMU. And we can directly write down that mass of proton is given as 1.0072767 AMU. We have NP also. What is Mn? Here it is clearly mentioned in the numerical that mass of neutron, that is M small m. The mass of neutron is 1.00866,490 AMU. So I just write down here So it is 1.00866,490 EM. So it is also given, Mn is also. What is capital N? Capital N is termed as actual mass of nucleus, and it is clearly given that actual mass of nucleus is this one, 4.00150,608. So we just write down here. Capital N is given as 4.00150,608. See this numerical very broadly, then from the next numerical we do it fastly, so our time will be same. Now see this one. So in this question, we have to calculate the mass defect and binding energy, and for the mass defect, that is del M, I should have the value of Z, the value of MP, the value of capital N, the value of capital Mn, the value of capital M, and I have all those values. So first of all, this Z is what? Z is 2. It should be multiplied first of all by Z and P. So NP is what? 1.00727,647. So I just write down 1.00727,647. And plus it will be added with NMN. So what is N? N is your 2. That will be multiplied by, which 2 will be multiplied by again Mn. So what is your Mn? Mn is given as 1.00866,490. Now this bracket will be closed, and this is your calculated value of nucleus minus capital M. And what is capital M? Capital M is directly given as 4 point, that is actual mass of nucleus, 4.00150,608. Okay. So by calculating these all, we can easily calculate the value of mass defect. So with the help of calculator, I just calculate this value and write down the answer of this. So first of all, whenever this 2 multiplied by 2.00727,647, that will be multiplied by plus 2.2 multiplied by 1.00866,490. So this will be 4.00. This will be 4.03188,274. And this will be minus by actual mass, that is 4.00150,608. So when we will just subtract these two terms, with the help of calculator, we can easily do this. 4.03188,274 minus 4.00150,608. So we can easily find out 0.03037,666. Okay, so we will find out the answer as, finally the mass defect is 0.03037,666 AM. So this will be the answer of this question. First answer of this question, that mass defect, we have to calculate the mass defect, and I calculate the mass defect as, this one is my first answer. This one is my answer first. That is, I calculate the mass defect. So I calculate the mass defect. So mass defect is 0.03037,666 AM. Now what is the binding energy? What should be the binding energy? So the binding energy is, we should multiply this. We know that formula of binding energy, that it should be, the mass defect should be multiplied by C square, that is 931.5 mega electron volt. I just copy the formula from the previous slide So binding energy we can easily calculate in terms of mega electron volt. If I just multiply this mass defect with 931.5 mega electron volt. Binding energy formula is this one. So I just to calculate the binding energy. So I just use this formula. So binding energy is equal to this del m multiplied by c square. I am talking about this formula. This del m, that is binding energy. So binding energy is this one. I just copy this binding energy. 0.03037666. It will be multiplied by your 931.5 mega electron volt. So 931.5. What will be your final answer? So just to multiply this, so do it on calculator again. So when we just multiply on calculator this 0.03037 multiply by 931.5 mega electron volt, it will be 28.2958588. The unit is mega electron volt. So this is answer number second. This is your answer number second. So this is my answer second. That is the binding energy. This is the binding. So we complete with the help of the concept of mass defect and binding energy the total numerical that is in front of you. So now let's do one more numerical on this side. I just save this file and we are going to calculate the second. So let the numerical is, we have to calculate the same thing, binding energy and mass defect. So I just write down so in a short term so you understand that what we have to do in this numerical. We have to calculate the mass defect. So I just write down with question mark the formula, the abbreviation for mass defect, that is del F. And we have to calculate the binding energy. So as an abbreviation in short form, I just write down B, that is binding energy. And with question mark. So we have to calculate these two things. What is given? We have to calculate this thing for the lithium, and we know that lithium atomic number is 3 and its atomic mass is 7. So I just write down lithium is given 3 Li 7. Okay. Now we have to, it is also given that the mass of the proton is, the mass of the neutron is, and the mass of the nucleus is. These three terms are also given. The mass of the proton is given as 1.007825. 1.00725. The mass of the neutron is given as 1.008665. The atomic mass of the nucleus is given as 7.0000. 7.0000. So these three terms are given. It in certain numericals, it may frequently ask or frequently given in the question that the mass of the nucleus may be not given the actual mass, they given some something apart from this actual mass of 7. Let they will give 7.2537. So in numericals, whatever the value is given, you should put that. Okay? So now we have to calculate the mass defect and binding energy. So directly I am going to solve this question because we understand till now that what are those indication towards aggregation means. So what is the value of Z? So Z is your 3. Z is my 3. So the I should use the perfect formula. So directly I copy the binding energy formula from this or mass defect formula. So mass defect is this one. And when it will multiply by 931.5, then automatically the binding energy will come. So what I have to calculate the mass defect. So mass defect is my this one, ZMP plus NMN. Okay. One person, Sagar Kumar, have already been solved this question and sent the answer of binding energy previous question. So that was correct. That is very good. In chat box, I just see. So here, what is my Z? So Z is definitely this one, which is given as an atomic number. Hydrogen, lithium. So lithium is at 3. So this is Z. So Z is my 3. So I have to multiply this 3 by mass of proton. So mass of proton I directly write down. So mass of proton is given as 1.00. 1.007825. Then this term will be added with NMN. So what is N? So N is what? This lithium. This atomic number 7 is actually your A. So I know the capital N can be calculated as A minus Z, as in the previous example. N. So that is 7 minus 3. So that is equal to 4. So N is my 4. So this 4 will be multiplied by Mn, and Mn is directly given as mass of neutron. That is 1.00. So I just write down this value 1.008665. 8665. This and Z and P and N and Mn will be multiplied by add with each other and subtract from by capital M, that is atomic mass, and it is given that is 7.000000. So we have to calculate this value, and when we will use the calculator to calculate this value, I am going to calculate these two values. So what will be the answer of this bracket term? So 3 multiplied by 1.007825. So it will be equal to 3.023475. So it will be added with, I just write down the final answer, 4 multiplied by 1.0086668664. So the answer of this one is 7 point, I just write down here. So this calculated mass of the nucleus will be by Z and P plus N will be 7.058135. We have to subtract this with actual given mass, that is 0.00000. So as a result, we will find out that the mass defect, I just increase the size so you will easily see this one. So now the actual mass this will be equal to, when I just subtract, so this will be 0.058135 atomic mass, 0.058135 atomic mass, and this is my answer of this question. The first answer is mass defect. So this is first answer, that is atomic mass. That is mass defect. Okay. Now I have to calculate the binding energy. So as I already told you that binding energy can be easily calculated if I just multiply this mass defect with 931.5 and mega electron volt. Yes. So whenever this mass defect will be directly multiplied by this 931.5, then automatically we will find out the binding energy. And here for this question, I just calculate. So I have to multiply this 0.058135, and this will be multiplied by. So this star is out to show you the multiplication sign. Don't be confused. 931.5. So this will be equal to, I just multiply by these two terms. When this will be multiplied by 931.5, then it will be 54.15. 54.1527525. So over 54.15, I just write down mega electron. So this will be the answer of this question. This will be the answer of this question of how to calculate the binding energy. So for these two questions, we solved the binding energy. If let's suppose someone asks you for graded kind of questions. If someone asks you that what is the binding energy per nucleus? What is the binding energy per nucleus? So how to calculate the binding energy per nucleus? Then we should divide the binding energy by the total number of the actual number of protons and neutrons present in the nucleus. Then we will calculate the binding energy per nucleus. So I just write down the binding energy per nucleus. So what is the binding energy per nucleus? What should be the value of binding energy per nucleus? So binding energy per nucleus can easily be calculated by binding energy divided by, here I just write down B as the abbreviation for binding energy. You can use B dot E dot also. Be confused. Okay. So binding energy divided by total actual number of protons and neutrons, or total number of protons and neutrons present in the nucleus, and we have already been abbreviated that total number of neutrons plus total number of protons. So total number, actual number, sum of those two as abbreviated by A. So when this binding energy divided by A, then we will calculate the binding energy per nucleus for any kind of numerical. So if someone asks you, or it is you have to, it is given that you should calculate the binding energy per nucleus, then you should use this formula number third, that is the binding energy divided by sum of the number of neutrons and number of protons present in the nucleus. So for this numerical, let's suppose I have to calculate the binding energy per nucleus, then definitely for this question I have to divide this binding energy, that was my 54.54 mega electron volt. So 54.54 divided by the total number of protons, sum of proton plus and neutron, sum of proton and neutron, or total number of proton and neutron present in the nucleus. So here what is A value? So A value I just encircle again with this orange color. So this is 7. So I have to divide this by 7, and I will find out the final answer of this number of binding energy per nucleus. The unit will be same as mega electron volt. So for 54.15 divided by 7, that will be 7.7357142. So I just write down 7.735. 7.735. I just write down. 7.735 gigawatt. This is your binding energy per nucleus. Let we wish to calculate again in the previous example the binding energy per nucleus. Then we can easily calculate binding energy per nucleus for this numerical, the previous numerical also. Binding energy. So we know that binding energy per nucleus will be equal to binding energy divided by E. So here for this numerical binding energy is 28.2958588. So I just write down as 28.2. Okay. So divided by A. What is the total A? So C, it is given as 2He4. So 2 is your number of protons. A, that is equal to number of protons plus number of neutrons that I require in this formula at the place of A, that is 4. So I have to divide it by 4. So I will find out as binding energy per nucleus for the 28.29 binding energy divided by the total number of neutrons and protons present in the nucleus. So that will be 28.29 divided by 4. That will be 7.0725. 7.0725. And the unit is same giga. This one is the answer for this binding energy per nucleus concept. Okay. So here this is this was your answer number 6. So that's all about your binding energy and mass difference. The basic definitions, how to calculate in the formula, what are those different abbreviation means in the formula, and how to you solve the numericals. Now we are going to solve certain objective questions related with the binding energy and mass difference. So the frequently asked questions are, I'm just coming with those frequently asked questions. Wait for a while. So what kind of numerical objective questions come? So see in this new slide. First of all, the frequently asked questions are related with the general formula. That what is the which one is the correct representation of the binding energy, right? So if the atomic mass number is this, atomic unit is this, atomic mass number of this is this, then what will be? How we can calculate? Okay. So now see. Yes. Okay, it is given that we should calculate the mass defect for 37 atom for which the actual mass is 36.966. So how we can calculate? Okay, it is given. Yes, yes. I just write down this one. So we'll not calculate. Okay. First of all, calculate mass defect for 5 B. Here. If actual mass is actually that is present on Google, which I want to show you on this question being, but that cannot be copied by me. That can it is not given that you should copy that. So I just type that. So if actual mass is okay, so you should calculate the mass defect. So apart from the basic objective of A, B, C, D, can anyone among you solve this question and send me the answer? First I write down the total. I calculate the mass defect for a 5B11 if actual mass is 11.0003 AMU. The mass of electron and proton which is given for this question is, let's suppose I should choose the previous slide, mass of protons and neutrons, no problem. Apart from this, because that question is present on Google, that's why. So let's suppose the mass of proton is this one. Okay, you have to solve instead of an objective. If you are going to solve a numerical, then how to solve those numericals? This third numerical, see this one. The mass of proton is 1.00727646. Mass of neutron is 1.007825, 1.00727, 1.008665, 1.0086665. So you should calculate for this what should be the value of your mass defect. Then try to solve this question and find out the answer. I just wait for a minute, otherwise I will start. Yes. So the objectives which are given, because all the objective looks like similar, that's why I did not type them. The answer is point is 0.99654. Any the objective B is 0.89776. Any the third objective is 0.088074. MU. The objective B is 2.9800 PM. So, can anyone tell me that which one is the correct answer for this question? 0.08807. Very good. All of you are very correct. Option C. Yes. So the answer is C. Actually, that this question is directly present on the Google, but I am unable to copy from them because that is not easily copied. So I just type in message box and I calculate for myself from the calculator then, because we have to check previously. Okay. So this one is numerical number one, but you easily understand that what kind of numericals come in front of us. Okay. So now the second question is, a nucleus has a mass number A, atomic number is Z, and binding energy is B. Okay, binding energy is A. The mass of neutrons and protons are ms and mn respectively. Okay. And c is the speed of light. That's fine. Which of the following expression correctly represent the mass of the nucleus? Okay. This can be copied. So now see the second objective questions. Can you easily solve this question? Use your knowledge, then you will find out that you can easily solve this question. Just to decrease some font size. Yes. So a nucleus has a mass number A, atomic number Z, and a binding energy B. The mass of neutrons and protons are Mn and Np. Here the Mn, the N is in subscript, okay, and P. So P is in subscript, don't be confused, respectively. And C is the speed of light. Actually, this C is C, and there is some gap. C is the speed of light. There is some gap. Okay. Which of the following expression collectively represent the mass of the nucleus? So, okay, A minus A is the and yes. Okay, I write down the answer as we have already been done this. A is the correct answer. Why? First of all, why? Z and P means mass of proton multiplied by number of proton. That's fine. Mass of neutron multiplied by number of neutron, and number of neutron can be calculated as A minus Z. Then there should be a sign of minus. Here that is plus, so the B option is incorrect. The C option is also incorrect. And C, here for calculating the mass of a number of neutron, it used the formula A plus Z. So this one is also incorrect. So definitely the answer will be A. We can directly find out otherwise. Minus capital M, that is the mass of nucleus, and we know that binding energy is equal to del M multiplied by C square. Del M multiplied by C square. So del M is equal to binding energy divided by C square. So binding energy divided by C square is your can also be termed as actual mass here, okay, because actual mass is not directly given. So we can use that one as actual mass. So option A is correct. So these kind of objective questions frequently asked in examinations. Let's come with another example. Okay, so these kinds of objective questions frequently asked in examinations, somewhat, but all those objectives are related with the numerical approach. That's why I do not want to copy here, because we have already been done two numericals and one more numericals in the first objective questions. So these kind of numerical same objective questions are frequently asked. Apart from those, if the objective contains that if the which one is the correct formula, like this one, so you can directly write down those. What should be the value of C square, which will be multiplied by the mass defect to calculate the binding energy, and that is 931.5 mega electron. Okay, so I think you understand this mass defect and binding energy concept and how to solve the numericals related to the mass defect and binding energy. So thank you for watching the video. I Rakesh Jain from the Cambridge University wants to say thanks to watch this video. Thank you very much.